Rates of chemical reactions is part of the Flipped Learning in General Chemistry series. In this video, we'll explore the concept of a rate and see how to measure the rates of changes of reactants and products during the course of a reaction. After doing the assigned problems, you should be able to define the rate of a chemical reaction, determine a rate from a plot of concentration versus time data, including average rates over a time interval and instantaneous rates at a specific time, and finally, you should understand how the overall rate of a reaction depends on a balanced chemical equation. A rate is a measure of how some property varies with time. The rate of a chemical reaction is the change in the amount of a reactant or product per unit time. Usually the amount is expressed as a concentration, and this plot shows how the concentration of A is decreasing with time in the generic reaction of molecule A turning into molecule B. The average rate can be calculated from the change in the concentration of A divided by the time interval delta T. During the first 5 seconds of the reaction, the concentration of A decreases from 5.0 to 1.8, which is a change of negative 3.2 molar. Delta T is 5 seconds, so the average rate is negative 0.64 molar per second. You can see from the curvature of the plot that the rate of the reaction is not constant. In the next 5-second interval, the concentration of A has only decreased by 1.2 molar, which means the average rate has slowed to negative 0.24 molar per second. The rate of change of A continues to decrease in the third and fourth intervals on the plot. Another way to express the change in concentration of reactant A is the instantaneous rate dA dt. If the plot represents the function A of t, then the first derivative is the slope of a tangent line at a given point. Here's the tangent to the curve after 5 seconds. The slope is negative 0.37 molar per second, which is the rate of change of A at this instant. Just like the average rate, the instantaneous rate of reaction is also decreasing with time. After 10 seconds, the slope of the tangent has decreased to negative 0.14 molar per second, and it continues to fall as the reaction proceeds towards completion. We will use both average and instantaneous rates of reaction during our discussion of kinetics in class. Now let's look at another hypothetical reaction that has two reactants and a stoichiometry of 1 mole of A reacting with 2 moles of B to make 3 moles of C. Shown here is a plot of the reactant concentrations, A and B. There's no limiting reagent in this problem. Both A and B are consumed completely, so their concentrations approach 0 at the end of the reaction. To achieve this, we had to start with twice as much A as B. Let's see how this stoichiometry affects the rate of change of each reactant. We'll pick 5 seconds and determine the instantaneous rate of change for both species at this point. dA dt is negative 0.07 and dB dt is double that at negative 0.14 molar per second. And this makes sense. B must be consumed at twice the rate of A because twice as many moles of B are used during the reaction. Now let's add the concentration of C. The first thing you notice is that this curve is increasing because C is the product of the reaction. It's approaching the theoretical yield of 3 molar. The tangent to this curve gives us the instantaneous rate for C, and at 5 seconds the rate is positive with a magnitude of 0.21 molar per second. The 3 rates that we've measured at 5 seconds are called relative rates, and they're related by the stoichiometry of the balanced equation. B decreases twice as fast as A because twice as many moles of B are consumed. The product C forms 3 times as fast as A because 3 moles of C are formed for every 1 mole of A. Notice also that the reactants have negative relative rates while the products are always positive. We need to be able to define a single overall rate regardless of which reactant or product we're talking about. We do this by multiplying the relative rate by 1 over the stoichiometry coefficient. So the overall rate for this reaction is 1/3 the relative rate of C at a given point. This is equal to negative 1/2 times the relative rate of B, or negative 1 times the relative rate of A. You can use any species in the reaction to define the overall rate. At 5 seconds, the overall rate of this reaction is plus 0.7 molar per second. Now it's time for you to practice estimating rates on your own. Here's a plot of the disappearance of dinitrogen pentoxide as it decomposes to nitrogen dioxide and dioxygen. Estimate the average rate of change of N2O5 during the time intervals given, and then use the balanced equation to calculate the overall rate for the reaction. After that, you can calculate the average rate of formation of NO2. Use the tick marks on the y-axis to estimate the concentrations as accurately as you can. During the first 20 seconds, the concentration of N2O5 decreases by about 0.008 molar, which gives a rate of -4 times 10 to the -4 molar per minute. The overall rate of the reaction is -1/2 times the rate of N2O5, which equals 2 times 10 to the -4. The rate of formation of the product NO2 must be 4 times the overall rate, or 8 times 10 to the -4 molar per minute. Between 40 and 80 minutes, the N2O5 concentration decreased by about 0.004 molar, which gives a rate of -1 times 10 to the -4 molar per second. The overall rate of the reaction is 5 times 10 to the -5, and the rate of NO2 formation is 2 times 10 to the -4 molar per minute. That's it. Don't forget to complete the problem set and read the textbook sections assigned with this video. You should come to class prepared to determine the rates of reactants and products in a chemical reaction. Thanks for watching.